multiplies like across down, right? So it's AK plus BM, AL plus BN, and then CK plus DM, and CL plus DN. And often what happens is that you're told that that's the way you multiply matrices, but never given any reason why people came up with such a weird way of multiplication. Because, you know, if you think about it, another natural way to multiply would be just simply A times K, B times L, C times. What's wrong with that, right? And there's nothing wrong with that. That's another kind of multiplication you can do. But it turns out that there's a reason why we like this multiplication. And there's a reason why a lot of the other types of math eventually can be expressed using this multiplication. So I want to take some time today to explain that. Right? So first of all, let's think about transformations on the plane. So like what kind of transformations take shapes to another shape? So you can move a shape to another one. So there's like something called translations, right? What's a translation? It's a function that takes x and y, and then it spits out by adding some values in both cases, right? X plus a and then y plus b. That's a translation, right? It moves 1 point by, say if this is like 2 and 3, then it moves 2 to the right and then 3 up. That's what's happening. You can also have something called a reflection. There are many examples, but let me just give you one. What happens if you have x comma negative y? What does this do? Yes?
It becomes negative x positive y? For like reflection?
No. It's a reflection over what? That's my question.
Oh.
Is it reflect? Yes.
It's a y-axis?
X-axis. It's a reflection over x-axis because just try to test on one. Say you have 2 comma 1. Now if you apply this, what happens? It becomes 2 comma negative 1, which is over here. So it flips over the x-axis. So this is this one right here is a reflection over the x-axis. That's how it is. Okay, and then you can also have rotations. Now, rotations in general is quite complicated. So I don't want to write the formula for the rotations in general. I'll just use something simple, which is like, say, f of x comma y. If you send this to y comma negative x, let me see, what does that do? If I put 2, 1 into f, this takes it to 1 comma negative 2, right? What's that? 1 comma negative 2. So we went from here to here. So what's that? That's a rotation by negative 90 degrees. Because we usually talk about positive angles to be counterclockwise. So if something rotates this way, we say it's negative 90 degrees. Okay? So that's a rotation in negative 90 degrees. Well, if you're interested in how you do rotations in arbitrary theta degrees, let me write it. You don't have to know this. It's something like this. It's x times cosine of theta minus y times sine of theta, and x times sine of theta plus y times cosine of theta. This will rotate anything by theta degrees. Which you don't have to know, okay?
rotations?
Hmm?
We don't have to know rotations at all?
None of these you have to know. There's nothing for an exam. I'm just trying to explain why that's true. But if you follow my logic here, you'll kind of gain more understanding of why matrices are multiplied that way. And then, in turn, you'll see why other properties hold. Right? So, rotations, reflections, and translations. And there's something called a glide reflection where you move and then reflect along that line, something like that. Those are what's called affine transformations, which are things that, rigid transformations, by the way. Rigid transformations are things that would take a shape and move it to another shape without changing its size or the shape. Okay? Those are rigid transformations. But then, there are some other types of transformations on top of this, which is called expansion or contraction, expansion. So these are like if you have f of x comma y, so 1/2 x, 1/2 y. What would this do?
We shrink it.
Shrink it by half, right? So if you have 2 comma 2, this point here, if you put 2 and 2, you end up with 1, 1. So you get 1 comma 1. So with respect to this line that was here, this entire line will be shortened by a half. Okay? So everything will be shrunk down by half, as if you put this shape in the copy machine and you put 50% and you Xerox it, and then you end up with something that's half size, right? So that's what you. If you put 2 instead of 1/2, will be doubling. Right? So those are the things. Okay, so those are some transformations you can think in the plane. And this function here, when we say transformation, it's really a function from pair of numbers to another pair of numbers. So that's what we are talking about when we say transformations. Okay. Now there are many, many more transformations than the ones that I just told you. So for example, you could take any picture. Okay, let's say this is my crappy drawing of Mona Lisa, right? That's my Mona Lisa. Okay. So and then what I do is I take this line and then maybe another line like that, okay? And then I can shrink in one direction and expand that way, right? So these points will be like something like this, but then you have some really crappy looking transformed Mona Lisa. I don't even know how to draw it. Just use your imagination, right? And that one can also be written in some format like that. And all of these transformation is just some translation plus some linear transformation, but I didn't explain what linear transformation is. Okay, so let me just say something about these functions from R2 to R2. Functions from R2 to R2. That's my cryptic way of saying R is real numbers. And if I had to say R2, that means pair of real numbers. So you have some number here, another number here. So you have X and Y being sent to another one, and there's some formula for X and Y. Right? That's our transformation. And we say, definition, we say that a function f is a linear function if f of xy plus zw is equal to f of xy and f of zw. In other words, if you have two vectors and you're adding them, right? Same as applying the function separately. Okay? And f of some constant times xy gives you c times f of xy. Now, some of you may have noticed that this is very similar to the linear operator that I was talking about in differential equations, or even in calculus, we often say integration is linear, right? If you have integral of two functions, right, f plus g, the same as integral of f plus integral of g, right? And if you have an integral of some constant times of f, say the same as just like that, right? So those are some things that we already learned in calculus. That kind of property is called linear. Now what happens is that you can actually determine what the shape of a linear function from R2 to R2 will look like. So let's just think about the following. Let's say somebody gave you a function from R2 to R2. They just gave you, they say what this is, and they say it's linear, okay? But they refuse to give you the formula. Okay? So you ask just two questions. What's f of 1, 0? Okay? They say, oh, it's a comma b. Okay? And then the next question is, what's actually, for some reason, let me write this as a comma c. You could write it as a comma b, but just for the future calculation, I want to call this one as c, okay? And then you ask the next question, what's f of 0, 1? What's that? B comma d. Let's say you're given this, okay? And then they're very protective of their formula. They don't want to let it out, okay? But you already figured out what their formula is. How? Well, think of it like this. If you have x comma 0, then you can think of this as x comma 1 comma, x times 1 comma 0, right? Where x is a number, it's multiplied by as a scalar multiplication. But then according to this formula here, I can pull the x out. What's that? This f10 is AC, right? So it's x times AC. So it's going to be AX CX. Right? Then we're also going to do f of 0 comma y. I know how to do this as well, because now this is f of y times 0 comma 1, which is y times f of 0, 1. What's that? That's y times b comma d. So it's going to be by and dy. Okay? Now we're almost there. Now we just have to figure out what f of x comma y. That will be the full formula, right? How would we do this? We think of f of x comma y as? Any ideas? We're almost there. X comma 0 plus 0 comma y, which according to being linear, it means that it's f of x0, right? And f of 0y, right? So what's that? I already know these formulas. It's going to be this plus this, which means it's ax plus by, cx plus dy. Okay. So that's the generic formula for a linear function from R2 to R2. Yes?
This would be x, right? F of x of 0.
X0. Yeah. Okay, this is how a linear function from R2 to R2 should look like. Every one of them should look like that. You just need four numbers. Okay. And one thing that you should notice is that translations are not part of this, because to be a translation you should add a number, but that's not included here. But the rotations, all general rotations, reflections, those are included here. And even that ugly Mona Lisa picture, that also, you'll see later in this class that those kind of transformations fit in this category, okay? All right. So that's what a transformation looks like from R2 to R2. And then from here, let's talk about function composition. Now, some of you might not remember what that means. If you have one function that does 2x and another function that does 1 over x, what's f composed with g of x? 2 over x, right? It's just f of g of x. So you're doing f of 1 over x. But what's f of 1 over x? It's just like emptying out x and putting the 1 over x in there, right? So this is like 2 times 1 over x, which is 2 over x. Now on the other hand, what's g composed with f?
1/2.
Yeah, 1 over 2x, right? It's g of f of x, where f of x is 2x, so it's g of 2x. That's like, how do you do g of 2x? That's like taking this definition and writing in 2x in there. So this will be 1 over 2x. Okay, so function composition is not commutative, and it will mean something later, okay? But that's how you compose functions, right? Now what we're going to do is we're going to take 2 of these functions and compose them. And I want to show you how it looks like. So if you have f of xy, let's say f is a linear function, ax plus by, comma cx plus dy. And let's take another operation, gxy, and let's say this is like kx plus ly. Kx plus ly, and then mx plus ny. Okay. So that again, k, l, m, n are numbers like a, b, c, d. So if you're given 2 linear functions from R2 to R2, one should look like that, and another should look like another one of these. So with the different numbers, so instead of using a, b, c, I'm using k, l, m, n. These are just some numbers. Okay. All right. Let's now compose them. F composed with g of xy. What's that? Well, that's like f applied to g of xy. And I know what g of xy is. That's kx plus ly, mx plus ny. Right? Okay. Now what do we do? Now this goes into x, right? And this thing goes into y. So be let's do this carefully. Since this is replacing x, any x's that you see over here will be replaced by kx plus ly. Is that good? All right. So what you have is a times kx plus ly plus b times y mx plus ny, comma, c times what? Kx plus ly plus d times mx plus ny. Okay? So that will be the result of the composition of two functions. Now let's carry on here. This will be ak plus bmx. Is that right? ak plus bmx. That will be al plus bny. Then you have ck plus dmx. Then cl plus dny. How's that? What do you see? What do you see from here? This result should tell you something. What do you see?
Is that the matrix multiplication?
It's really the matrix multiplication. Right? It's exactly the same. AK plus BM, right? AK plus BM, AL plus BN, AL plus BN. It's exactly that. All right? So, I think Sylvester and some others were working with matrices. I mean, if you think about it, when Gauss first came up with the matrices, he didn't have any operations on them, right? Matrices are just array of numbers, okay? And that's it. Well, he didn't think about any operations. But then, Sylvester and some other mathematicians looked at this and said, well, I would like to allow matrices to be multiplied, but not in an obvious way, but in a strange way where it mimics composition of functions. And that's very nice because, for example, let's say you wanted to reflect over the x-axis. What was that? It's x comma negative y, right? That's the formula. So I want 1, 0, 0, negative 1. Now this is going to be a reflection over the x-axis. Can you see that? Now why is that? Well, our convention is that a, b, c, d becomes the function ax plus by, cx plus dy. So under this convention that we're using, right, a is 1, that's 0, 0, negative 1, that's exactly x comma negative 1. Okay. And this is indeed reflection over the x-axis, right? Yeah. Or you can also just say that these matrices act on x comma y with this multiplication. Surprisingly, this works as well. There's a like that, that's ax plus by. This times this will be cx plus dy as a matrix. Okay? So that's another way to think about the matrices as transformations. Right? And this is a reflection over the x-axis. And let's say we reflect over the x-axis and then y comma negative x was the rotation by negative 90 degrees that we talked about, right? Now if you multiply these, what do you get? You get the combination of those two transformations done at once. And if you're curious to know what happens if you combine these two, you can just multiply this. This times this is 0, this times this is negative 1, this times this is negative 1, this times this is 0. And what is this? That takes xy to negative y, negative x. That's what it does. And this transformation is what's known as the reflection over the diagonal. Okay? Yeah. So reflection over y equals to negative x. Okay? If you reflect over like that, then x goes to negative x and y goes to negative y. No, just a minute. X goes to negative y, sorry. X goes to negative y and then y goes to... This is x, that's y, that's negative x, that's negative y. So y goes to negative x and x goes to negative y. What it does, it flips over the y equals to negative x. So you can see that if you take any point, reflect over the x-axis first and rotate by negative 90 degrees, it will give you the same point as if you reflected over y equals to negative x. Okay? So those are the cool things you can do. Yes?
So these people basically like did the proof in like a geometric sense.
Yeah, they came up with the formula for multiplication of matrices in a geometric sense. Now there are a few other things that you get out of this. So one thing is that you can sense that multiplication will not be commutative, because this is function composition. We just found out that function composition don't switch, right? And we can actually show that there are examples. We can come up with those. But you don't have to come up with examples. You already know that function compositions don't. Sometimes they commute, but in many cases they don't. So you kind of know that. Another thing that you know is that what do you call this function? F of xy equals to xy. What is that called? This has a name, an obvious name. Yes?
The identity.
Identity function, right? Because it doesn't do anything, right? The input and the output are identical, right? Now, can you rewrite this in terms of matrices? If you write this as a matrix, what would you get? 1, 0, 0, 1. So what is this? This is going to be the identity matrix. What it does is that under function composition, this wouldn't do anything. That's exactly what we observed. If we call this as the I, we see that for any matrix, A times I or I times A will just give you A. Okay? That's why you do it, right? Okay. So the mystery of multiplication of matrices, if you're ever wondering why people made it that way, can be explained geometrically. And once you do that, then a lot of the mysteries about like why does this work that way, why doesn't that work, or these other things is just solved naturally. Yes?
So you had mentioned that you could also multiply matrices like in a more like easier way. With, like,
Okay. So that one is like, so there's something called the dummy multiplication. Dummy multiplication, and it's like A, B, C, D times KL. I think they put something like some symbol here. I don't know what. KL, MN. And you write it as AKBL CMDN. That'll be like another way to say multiplication. Now, it does have some uses in some numerical mathematics, but they rarely get used. You never, it's safe to say, in most cases, 99.99% of the time, when you're using matrices and you need some kind of multiplication, this is not it. This is useless. There's like very small use case for that. This is used everywhere. So in a sense, that's why when we say multiplication of matrices, it's always this one, not the other one. Any other questions?